All right, welcome to Domain 2 of differential equations. In Domain 2, what we will be working on is tangent lines. That's right, you heard it here. Tangent lines are, well, it's something that you've seen quite a lot of over the last few months in this course. Remember that for tangent lines, you basically need two things to write a tangent line. You need a slope, and you need a point. And in calculus class, in order to get a slope at a point, one of the things that we use is the derivative, y prime, dy dx, f prime, just whatever derivative you're given or whatever derivative you have to find, that's where you can get your slope. All right, so what we're going to see is a few tangent line problems of pretty standard difficulty. They don't have too much that they can ramp up the difficulty on, but you might be asked to only write a tangent line. You might be asked to use that tangent line to make a conclusion. You might be asked to say whether the tangent line is an underestimate or an overestimate. So let's take a look at this particular problem right here, which, excuse me, I forgot to say, let me just reference my notes here. This particular problem is 2010. We're going to take a look at A. I think I'm starting out at 2010 A because I don't have an electronic copy of my 2015 problem that I would have given you first. So I'm taking a look at 2010 from Group A in Domain 2. All right, so let's do this. So in Part A, wants us to write an equation for the tangent line to the graph of f of x at x equals 1. Or y equals f of x. So we're given a few things up here. We've got one differential equation up there. The derivative, dy dx, is x times y cubed. Then we're also given this differential equation. This thing right here is the second derivative of y. In another problem, we might be asked to use that, but in this particular case, for the tangent line, we really just want to find two things. We want to find the slope, and we want to find the point. So the point in this case, they give that to us, x equals 1, and we can see right here that f of 1 is equal to 2, so that makes our point 1, 2. And then to find our slope, we're going to use the derivative. So dy dx equals x times y cubed. And at this point, my slope would be 1 times 2 cubed, which is 8. So my tangent line equation is y minus 2 equals 8 times x minus 1. And you don't need to simplify this if you don't want to. Although if you wanted to, you certainly could. You would distribute the 8, you'd get 8x minus 8. You'd add the 2, you'd end up with 8x minus 6. Okay, and that is that. Why don't you take a look at some of these tangent line problems, and if you have more questions on the next group, come back in for the next walkthrough when I'll be taking a look at one of the first ones from Group B. And as always, please make sure you're checking your answers as you go. All right, so in Group B here on Domain 2, I'll be taking a look at the problem from 2016, Part B. This is where the wording starts to get a little bit confusing to a lot of people. The initial problem is really simple. Here's a differential equation, just pure math. And then in Part B, it says, let y equals f of x be the particular solution to the differential equation up here, with the initial condition f of 2 equals 3. Write an equation for the tangent line to the graph of that at x equals 2. And then use your equation to approximate f of 2.1. Okay, so there's a lot going on here, but what I want you to zero in on is what they're actually asking you to do. Regardless of what it says in the first sentence, they're saying that they want you to write the tangent line to the graph of f of x at x equals 2. The stuff that they mentioned up here as the particular solution is them just defining what y equals f of x is. Y equals f of x satisfies this thing y equals f is a solution to that differential equation. They're giving it a name, and then they're asking you to find the tangent line to that by using the differential equation at the point that they give you. So in part B here, we're going to set it up the same way that we did before. We want to know our point, and we want to know our slope. Our point in this case is 2, 3. And our slope we would use our differential equation for. So dy dx equals y squared over x minus 1. So when we plug in our point, dy dx would be equal to, looks like we've got 3 squared over 2 minus 1. So that would end up being 9. So our tangent line equation would end up becoming y minus 3 equals 9 times x minus 2, which we could rewrite a little bit to be y equals 9 times x minus 2 plus 3. There's our tangent line equation. So that gives this part of the problem an answer. The next part of the question is it's asking us to use that to approximate f of 2.1. So tangent lines, what they do is they approximate curves, yeah? So there's a tangent line to this curve, and as you can hopefully see, near this curve, the tangent line is kind of close to that. So a lot of the times a tangent line is called a linear approximation, or a line that approximates the curve near a point. And what we're going to do is use this tangent line to approximate the curve at 2.1. So what I would write is f of 2.1 is approximately equal to y equals 9 times, and then I plug 2.1 in for my x. So that would be, let's see, 2.1 minus 2 is 0.1, so that would be 9 times 0.1 plus 3, which is equal to 0.9 plus 3, which is 3.9. You can box it up there. You could have also boxed it up right there. Remember, you don't need to simplify. Okay, and that's another tangent line problem for you. Do notice one thing though, you might be asked later on about how concavity affects your tangent line approximation. If you take a look closely at this drawing up here, you might see that this curve is concave down, and then the tangent line is an over approximation at that point because the tangent line is above the curve. That is a pattern that is true. If I were to draw a concave down, a concave up curve right there, and put a tangent line on it, you can see that near this point, the tangent line is an under approximation. So you can use concavity to say whether this number that you get from the tangent line approximation is an over approximation or under approximation. So part B doesn't ask that here, but it certainly could later on. And left to cool in the kitchen. The internal temperature of the potato is 91 degrees at time 0. So 91 degrees at time 0. Maybe we want to take that and just write it off to the side here. 0, 91 is a point. The internal temperature of the potato is greater than 27, okay. And then the internal temperature of the potato can be modeled by H that satisfies this differential equation right here. Okay, so this dH dt tells us the rate of change of the temperature of the potato. because it's a derivative, and then the temperature of the potato is represented by the variable h. There's just a lot of information to sort through here. The reason why I'm starting there is because in part A, we're asked to write an equation for the tangent line to the graph of h at t equals 0. And what you need to do, what makes this a more difficult tangent line problem, is you need to go in and find what your complete point is based on what they give you. So they say at t equals 0. They're not telling you at 0, 70 or 0, 105 or something like that. You need to see t equals 0 and go, okay, 0 is the t coordinate. Where can I find my h or my y coordinate? And as we locate it up here, at t equals 0, the temperature is 91 degrees. So we wrote 0, 91, so I'm going to write 0, 91 right there. The other tough thing about this problem is that in order to find the slope, we need to use our differential equation again. So dh dt equals negative 1/4 h minus 27. But in order to use this differential equation, you might be tempted to plug 0 in for the h, because you're used to plugging in x coordinates. However, h here is 91. H acts like the y coordinate. So what we want to do is plug 91 in for our h, and, well, take it from there. So let's do this. dh dt, when the temperature is 91 degrees, so at time 0, would have a slope represented by that. Now this is a no calculator problem, so this is either a little bit of mental math, or you would just take this slope and you don't need to worry about simplifying it at all. The actual simplification ends up being negative 1/4 times 64, which would end up being negative 16. So now we can use this slope to write our tangent line equation. So what we would do is we would write y minus 91 equals negative 16 times t, or excuse me, probably best not to use t again. Let's do x's and y's for our tangent lines here. X minus 0. And I might rewrite this a little bit. Y equals negative 16 times x plus 91. So there's our tangent line equation. We can box that up. And then for the approximation, the temperature at 3 seconds, which is the next thing this is asking us to do. Oh, excuse me, I underlined there. The next thing this is asking us to do is to estimate the temperature of the potato at time 3. So the approximate temperature of the potato at time 3, we can use our tangent line for. So that'd be about negative 16 times 3 plus 91. So that would be negative 48 plus 91. And negative 48 plus 91, you can either box that up, or you can do a little bit of mental math or math on the paper and see that it is 43 degrees. Either way. So there we go. So that's the first of the more difficult tangent line problems for a reason. You not only need to read through all that stuff about potatoes and temperatures and differential equations, but you also need to see that they only give you part of a point, t equals 0, and you needed to find the other part, the fact that this was 0, 91 was your point. And then you need to use that point and plug in 91 in for the h. And then once you have your tangent line, use it to approximate at a certain time. So actually quite a few steps wrapped up into what at first might look like a pretty little tangent line problem. All right, give the rest of them a go. And as you go, remember to check your answers. And if you got any questions, let me know.